In this video, I'd like to talk to you about uniform circular motion. And in particular, we're going to talk in detail about a specific problem, a little contrived, but it will get the idea across. So I want you to imagine a cat tearing around the circle, maybe in the living room, just doing what cats do best. And the radius of the circle is 1.2 meters, and the cat goes around the circle once every 3.6 seconds and goes around counterclockwise. So if the cat started here at A, it would go around in this direction and all the way around once in 3.6 seconds. Of course, if you wanted to know how much time it took to get from A to B, then it would just be a quarter of that, because A is down below the center. Oh, this is like a view from the top down. So A is I guess, south of the center of the circle that the cat is running in, and B is east of the center of the circle. So I put a little compass rose at this diagram. I know most people don't have these in their living room, but it helps for describing direction. So just to get a feel for how circles work, to remind you of some things that maybe you knew once and might have forgotten, how about we try to figure out what's the circumference of the circle? So you might remember that circumference is the distance all the way around the circle. And there's a simple formula for it, that the circumference is equal to 2 pi r, or pi times the diameter, because the diameter is equal to twice the radius. So we know the radius of the circle because that's given. That's 1.2 meters. And so figuring out the circumference is as easy as plugging in the numbers and doing the multiplication. You can pause the video to see if you get the right answer, or you can just watch and follow along. But I think if you plug the numbers in that were given, 1.2 meters for the radius, we end up with the distance being around 7.5 meters for the cat to go around the circle once. Now how about a related question about how fast the cat is running? So if he goes around the circle once every 3.6 seconds, how would you answer the question, how fast is the cat running? So fast is not a very well-defined kinematic quantity. It's not like velocity. You might remember that fast is more like speed, and that speed is equal to distance divided by time. It's not so much a formula as it is an idea. If you want to know how fast, then you want to know the speed. And if you want to know the speed, you need to know the distance and the time it takes to cover that distance. You know, if the cat started here at point A and ended here again at point A, you could make the case that the speed of the cat is 0 because it started where it ended and didn't really go anywhere. But that's not what fast means in this context. Speed captures the idea that the cat traveled in a path, and you want to know how fast is the cat going along that path. So we're going to need the distance, but the distance is the once around distance, the circumference. And we're going to need the time, but we're given that the cat takes 3.6 seconds to go around once. So if we want to know the cat's speed, we can just do distance divided by time. Again, you could pause the video and calculate yourself to see what you get. But if you just plug in the numbers that are given, you end up with an answer that the cat is going 2.3 meters per second. So that's all well and good. Maybe it's just a warm-up for what we really want to know. What if the question was a bit more specific? And that is, what's the cat's velocity at point A? And also, what's the cat's velocity at point B? We really want to know if they're the same or not. That's the whole point of this video. So how do you answer a question about velocity? If you remember, velocity is a vector quantity and it needs two parts. It needs both the magnitude part, which is the amount, or the speed in this case, and it needs the direction part, the direction that the cat is moving. So what would you say for the velocity of the cat at point A? To me, it seems pretty clear that the velocity, the magnitude part of that, is the speed we just calculated, 2.3 meters per second. And the direction of that part, maybe we just have to reason out. So I think it looks like this. At point A, the cat's speed is 2.3 meters per second. And if he's going counterclockwise around that thing right here at point A, he's moving tangent to the circle. So this is his velocity here at point A. Tangent to the circle in the counterclockwise direction. And notice what direction that is. That's easter. That's to the east. What about at point B? What's the cat's velocity at point B? Do you think it's the same or different? You should make a guess before I flick the next slide, but I think you're going to catch on pretty quickly. That in fact, the cat's velocity at point B is going to be 2.3 meters per second, but the direction is different because up here at point B, the cat's moving, again, tangent, sort of like this, I guess. So at B, the cat is moving tangent to the circle in the counterclockwise direction. So at B, that's northerly. And then at A, the cat's moving 2.3, so the length of that vector is the same, but its direction is different. So easterly for B, east for at A, and north at B. What would you say about whether or not the cat is accelerating? So acceleration is a well-defined kinematic quantity. Remember what acceleration is. It's change in velocity divided by change in time. So I guess you have to ask yourself, is the velocity changing? That would be a yes or a no. Now, you might be thinking, well, here, 2.3 meters per second at A, and at B, also 2.3 meters per second. So it doesn't seem like the cat's speed is changing at all. And in fact, the cat's speed is not changing at all. But acceleration means exactly what it means. And anytime the velocity changes, then the object is accelerating. So even though the speed isn't changing between points A and B, the velocity is changing. The direction is changing. So the answer to this is most definitely yes. He is accelerating because the direction steadily changes. So the type of motion that we're describing here is called uniform circular motion. It's where something moves around in a circle and the radius of the circle stays fixed and the speed that the object goes around the circle stays the same. So in that particular case, we have to find a way to calculate what the acceleration is because our formula that we have for acceleration, delta v divided by delta t, might break down. So we're speaking here of a particular type of acceleration, and it's called centripetal acceleration. And I'd like to go through a quick slide here to show you how you could get to the formula for centripetal acceleration. But in the end, I think really what's going to matter is what the formula is. So the formula for acceleration is delta v divided by delta t. So we need to know what's the magnitude of the change in velocity. Although the speed is 2.3 meters per second, if we make a little triangle to show how these vectors are related, you can see that the magnitude of delta v, the thing that you would have to, so you start with v at A, you add the change in velocity and end up with v at B. So you don't have to know the details of this. Suffice it to say that we need to do, or you would need to do, a little trigonometry here on this abstract velocity vector triangle. It's really not important. Here, let's cut to the chase and get to the important stuff. You can use our formula for acceleration, delta v divided by delta t. That's the definition of acceleration. And if you work out the details of this vector triangle, you can show that in the case of an object moving around a circle at constant speed, then the acceleration turns out to be equal to v squared divided by r. So v is the speed that the object is moving in, and r is the radius of the circle that it's moving around. And this is called, again, centripetal acceleration. The reason why it's called centripetal acceleration is because it's always directed toward the center of the circle. Centripetal is, I guess, a Latin phrase that means center seeking. So the acceleration is always toward the center of a circle. If you stop and think about it, as the object moves around the circle here, v in magnitude isn't changing, but it's always getting pulled this way, if you want, toward the center of the circle. In any case, the centripetal acceleration, when something moves in a circle at constant speed, is equal to v squared divided by r, and it's always directed toward the center of the circular path. That's the take-home message for this. So it's really just a formula you have to know how to use and when it applies. And to reiterate, it calculates for you an object's acceleration if the object is moving around a circle at constant speed. So let's go back to our cat problem and see if we can calculate the centripetal acceleration of the cat. So remember that the cat is going around the circle once every 3.6 seconds. And we decided that its speed is 2.3 meters per second. So what if we want to calculate the magnitude of the cat's centripetal acceleration? It shouldn't be too bad. We just have to evaluate the formula v squared over r. So you can do that probably as well as I, but you might want to pause the video and plug in the numbers and see that you get the same thing. What are you going to plug in for v? 2.3 meters per second, and then you're going to square it. And after you square it, you're going to divide by the radius, which is 1.2 meters. So what do you get if you do that? I get 4.4 meter per second squared. Now the units even work out as well. So you would have, since the 2.3 meters per second, everything in there is squared, you would have meters squared per second squared. But in the denominator, there's a factor of meters, which cancels one of those out, and you end up with the very nice units, meters per second squared. So if you wanted to know at A, for example, what's the direction of the acceleration vector, it would be like this. And its magnitude would be 4.4 meters per second. If you wanted to know what was the acceleration vector at B, it would be like this, pointing toward the center of the circle, but its magnitude is also 4.4 meters per second squared. So the acceleration vector always points toward the center. If you were asked the question, what's the magnitude and direction of the cat's acceleration at A, you would say 4.4 meters per second squared north. And if you wanted to know the magnitude of the acceleration at B and the direction, the magnitude would be 4.4 meters per second squared, but the direction would be west because of the little compass rose, north, east, south, west. All right, and then lastly, how does this connect up with Newton's second law? Well, if something is accelerating, then there has to be a net force exerted on the object. So suppose the cat had a mass of 3.5 kilograms. And we wanted to know what's the magnitude of the net force exerted on the cat. How much force does it take for the cat to run in a circle at this speed? Well, we do know the same old thing that we've always known, that the net force is equal to ma. The mass of the cat is 3.5 kilograms, and the cat's acceleration is 4.4 meters per second squared. So we really only have to multiply those to get the cat's acceleration. of 15, the net force exerted on the cat of 15 newtons. Now it's interesting to stop and think about, where does this force come from? I wonder if we could imagine, if we looked maybe from this perspective, so an eyeball over here looking back this way, what would you draw for a force diagram for that? So I would see that the acceleration has to be northward toward the center of the circle, so there has to be a net force that's directed that way. So the net force is also directed toward the center of the circle. And for that reason, sometimes this force is called the centripetal force, the force required for something to move in a circle at constant speed. But in any case, a combination of forces often result in the proper force to keep something moving in a circle at constant speed. So there's a bit of a word game going on here. In any case, these ideas are in sections 5.1 and 5.2 of your book. And it's really not much harder than using this simple formula for centripetal acceleration, and then keeping track of various directions, knowing that the centripetal acceleration always points toward the center of the circle. And when something moves in a circle at constant speed, so does the net force. Always has to point toward the center of the circle.